Okay, in this segment we're going to start a brief foray into the territory of semiconductor device physics. And we're going to be developing some terminology and some concepts that will allow us to develop, at least in kind of a cartoon fashion, where the IV characteristics of our nonlinear devices come from. So diodes and transistors most notably. We're going to be doing this for a little while. There's a slide deck that you can download off the Canvas page if you want to do that before you watch the video. If you want to follow along and take notes or something on it, you might want to do that. But we're starting out here with a simplified periodic table of the elements. You may have seen some of this stuff in Math Sci or chemistry class or something like that. Hopefully some of it will be new, and even if you have taken a lot of chemistry and Math Sci, hopefully some of it will be new. Some of the terminology certainly will be new and specialized to sort of electronic devices. But if you recall, why do we group these elements into these vertical columns? So here, we've eliminated the transition metals from the table to simplify it. We've got the group 1 elements, the group 2 elements, the group 3, 4, 5, 6, 7, 8 elements. So what do these elements share in common along a column in the periodic table? Well, they share the same number of valence electrons. And if you recall, that's the number of electrons in the outermost shell of the outermost shell, and those electrons determine sort of the chemical properties of that particular element. So over here in group 1, we have a mostly empty shell, and these elements are very reactive. Over here at group 8, we have sort of maximally happy and satisfied elements, the noble gases, so-called noble because they don't react with anybody. In between here, we have these sort of group 4 elements, which are sitting sort of halfway between empty and full. And so these are, depending on whether they are glass half empty or glass half full elements, I suppose they have a different outlook on life than their neighbors or something. Anyway, so we're going to be focusing here on group 4 and silicon in particular, since silicon is by far the dominant element out of which we make semiconductor devices today. There are some compound semiconductors that are made from sort of a different group 4 elements like silicon germanium or silicon carbide. There are also other kinds of compound semiconductor devices that are made out of a group 3 and a group 5 element, like gallium arsenide or gallium aluminum indium phosphide, and that kind of thing. But by far, silicon is going to be the dominant technology by volume for sure. And so we're going to be focusing mainly on silicon. And what we have here is sort of a schematic representation of a silicon crystal. So the silicon crystal has a three-dimensional crystal structure. It's actually the diamond lattice, which it shares with carbon, which is its next-door neighbor one row up in the periodic table in group 4. And what we're showing here is sort of a flattened representation of it, where each silicon atom is sharing one of its 4 valence electrons with a neighboring silicon atom, and they participate in these 4 covalent bonds, gluing these silicon atoms together to form a crystal. And this type of pure silicon crystal is called an intrinsic silicon crystal. And at room temperature, or at any finite temperature, this silicon crystal lattice is actually always in motion. It's always vibrating. These atoms have thermal energy. These electrons are zipping around in sort of a shared molecular orbital that goes through the whole crystal. And so it's just a buzz with motion. And although these silicon atoms are more or less tied to a particular location in space, they're able to sort of move around that nominal position just by vibration. And every once in a while, what will happen is that you'll get enough thermal energy in a particular location that you can get one of these so-called valence electrons ripping out of its covalent bond and moving away from that location and leaving behind a vacancy. An electron that undergoes this sort of event is called a conduction electron because it's actually free to move around the crystal and conduct electricity. And it takes about roughly 1.1 electron volts to have this happen. And just as a sort of just to give you an idea of how unlikely this sort of thing happens to be, at room temperature, the average sort of thermal energy at room temperature would be something like kT, which is about 25 milli-electron volts. So 1.1 electron volts is actually quite a lot of energy compared to the average thermal energy of an electron at room temperature. So this is not a very likely thing to happen, but it does happen. One thing that you'll note here is that if we wait a while, well, what can happen is that electron will move away from its original site, and that movement of a charged particle is conduction of electric current. But we can also have a neighboring valence electron pop into that vacancy and fill it, and the vacancy is free to move. And so this vacancy, actually, if you think about it, is behaving sort of like a positively charged particle. Because what will happen is that the electrons move, the valence electrons have a tendency to move in an electric field in the same direction as, let's say, the conduction electron would. And so you'd have a tendency to want to fill that hole from over here. And so the hole is moving in the opposite direction. And so that would be behaving like a positively charged carrier. And so for bookkeeping purposes, we do consider holes to actually be a positively charged particle that is moving under, let's say, an electric field or something like that. And so you have both electrons and holes available to conduct current in an intrinsic silicon crystal. Now I mentioned that this sort of this event happening where an electron-hole pair is generated is a fairly unlikely event or an improbable event at room temperature. The concentration of these electron-hole pairs per cubic centimeter in intrinsic silicon at room temperature is around 10 to the 10th per cubic centimeter. Now that may seem like a lot, but if you actually compare 10 to the 10th per cubic centimeter to the number of atoms in a cubic centimeter of silicon crystal, it's actually not a whole lot, right? So there might be more like Avogadro's number of atoms in a cubic centimeter of silicon crystal. That's like 10 to the 23rd. And so this is happening at roughly 1 in 10 to the 13th lattice site. So it's not a very likely thing to happen. And since the conductivity of a material is proportional to the number of carriers that are available to actually carry a current under an electric field, the intrinsic silicon crystal is actually not a very good conductor at room temperature. But like chemical reaction rates, the number of these things that happen basically doubles for every 10 degrees Celsius increase in temperature. And so it doesn't take too many sort of 10-degree increases in temperature for there to be a whole lot more electron-hole pairs available than there would be at room temperature. And so if you actually plot the conductivity of a material like intrinsic silicon, you'll find that actually it follows an exponential characteristic with temperature. And so this type of material is called a semiconductor because it is somewhere between an insulator, which has very, very few electrons available to conduct electricity, and a metal, which has essentially an unlimited number of electrons, or practically unlimited number of electrons available to carry a current. And so the semiconductor can be a very poor conductor at lower temperatures, and it can actually be quite a good conductor at higher temperatures. And so that's sort of the baseline intrinsic silicon crystal. And I should say that because we've invested so much in the semiconductor industry, and because silicon is the workhorse of that industry, we are actually able, with astonishing repeatability, to be able to grow very large silicon crystals, single crystal silicon crystals, with astonishingly good purity, like less than parts per billion impurity levels, single crystal silicon ingots that are like a foot in diameter and like 6 feet tall. I may, later in the course, I may suggest you all watch a video where they show sort of a time lapse of that process, and other aspects of fabrication of these types of devices, and it's actually quite remarkable. But anyway, so that's the baseline. What we can do with silicon is to introduce impurities in selective locations. And so if we take, for instance, a group 5 element like phosphorus, and we introduce it into the silicon crystal, displacing a silicon atom, what will happen? The group 5 element has 5 valence electrons, and 4 of those 5 valence electrons will participate in covalent bonds with neighboring silicon atoms, just like the silicon atom that it displaced. But there's this extra electron that's hanging out here. And that extra electron, it turns out, is only very loosely bound to this particular latticite. It only takes about maybe 50 millielectron volts at to liberate this this loosely bound electron from the latticite. And so at room temperature, practically all of these phosphorus atoms, all these group 5 atoms, would have that happen. And by introducing each phosphorus atom that we introduce into the silicon crystal then comes essentially with a conduction electron. And so what will happen is that this phosphorus atom basically is able to donate one of its valence electrons to the cause of conducting electricity. So phosphorus is called a donor impurity for silicon. And what will happen when that electron is liberated from this attachment to the phosphorus atom, it becomes a conduction electron. And because this phosphorus atom went in charge neutral, there's an extra unbalanced proton in the nucleus here at this lattice site. And so we have here an ionized donor, which is positively charged, because we lost the negatively charged electron, uncovering this extra proton here. And this particular positive charge is sort of tied to this lattice site. So it's fixed in location, so it's called a space charge. Okay? So if we have a region of silicon where we have introduced these phosphorus or group 5 atoms more generally, we are said to have an N-type silicon crystal. So it's doped. Doping refers to adding impurities, and it's doped N-type because these extra mobile carriers that we're introducing are negatively charged. That's what the N stands for, negatively charged. Okay? So if we instead think about what would happen if we introduce a group 3 element instead of a group 5, we have a similar kind of thing, only this comes, it turns out, with a hole instead of an extra electron. So this boron atom, which went in charge neutral, has 3 valence electrons, and so those 3 valence electrons will participate in 3 of the 4 covalent bonds that the silicon atom that it displaced had taken part in. And that extra vacancy is basically a hole. And so that hole, just like that extra electron that the phosphorus atom had, was easy to liberate. This hole is easy to fill in. And so practically speaking, at room temperature, all of these holes get filled in, and this hole is then free to move around and conduct current, just like we talked about in the intrinsic silicon crystal. And so a group 3 element for silicon is called an acceptor because it's able to accept a neighboring valence electron. And if we dope a silicon crystal with a group 3 element, it's said to be doped p-type. So P stands for positive, and that's the charge, sign of the charge on the mobile carrier that we're introducing into this region by doping the crystal that way. And so here's a picture of the one of these electrons down here popping over and filling that hole in. The hole is able to move away. There is one extra negative charge that's left behind here. That extra electron, the valence electron that comes in here, is one extra negative charge in this vicinity. And so we're not uncovering a proton in the boron nucleus, but we have one more electron than we have positive charges in the boron nucleus. And so even though the actual electron that is sort of in this location may change from instant to instant as those electrons zip around in that shared molecular orbital, what will happen is that there is an extra negative charge here near this boron atom, and so this is an ionized acceptor here, and we have basically a negative space charge in this area. Okay, so that's impurities, N-type and P-type, donors and acceptors. And we can introduce these impurities at actually quite low levels and exquisitely tailor the conductivity of a region of silicon by over orders of magnitude. And so it wouldn't be unusual to introduce dopants at, let's say, a concentration of something like, I don't know, 10 to the 17th per cubic centimeter, or 10 to the 18th per cubic centimeter. And that's 7 or 8 orders of magnitude more than the intrinsic silicon crystal's concentration of electrons or holes. And so the conductivity would be 7 or 8 orders of magnitude better than silicon that's intrinsic. But if you think about what level of impurity this is, if we say it's 10 to the, let's say 10 to the 18th, and there are roughly 10 to the 23rd silicon atoms per cubic centimeter, that means the level of impurity that we're talking about here is 10 to the minus 5th. That's like 10 parts per million, which is a very, very low level of impurity. And so when we dope silicon crystal like this, we can control or change the electrical properties of the material to a very large extent, while we're leaving the mechanical properties of the material largely unchanged, which is amazing. And so we can create or tailor the electronic properties of these devices and still count on their mechanical properties being pretty much the same as that of bulk silicon. And so we have the possibility of making all kinds of interesting electromechanical systems. And so there are these systems called microelectromechanical systems, or MEMS systems, that have developed as sensors and actuators on a microscopic scale because of that. So we're going to review some very basic electrostatic relationships. We're going to need some of these to think about how charge and electric field relate to potential. And we're always going to be doing this in one dimension, and so I just want to review these basic relationships. So the first one is something called Gauss's law. And this is a relationship between the divergence of the electric field, which is del dot E, where E is the electric field vector. In one dimension, it basically becomes just dE dx, the spatial derivative of the electric field. And that's related to the unbalanced charged density divided by the permittivity. of the material. So this is a relationship between charge density and electric field. And then there's a relationship between electric potential and electric field, and basically the electrostatic potential is defined to be the negative gradient of, or the electric field is the negative gradient of the electrostatic potential. And so in one dimension that basically relates the spatial derivative of the potential to the electric field. And so sometimes we will combine these equations and come up with a second order equation for the potential and relate that to the charge density. That would be called Poisson's equation. And that basically says the curvature of the potential, which is the second spatial derivative, is related to the charge in a given region. And then the final relationship that we're going to make use of when we get to MOS transistors or MOS transistors is basically when we have two different materials with different dielectric constants or different permittivities, there's a boundary condition that relates the product of the permittivity to the electric field normal to the interface, and that quantity is called the displacement that's conserved across the boundary. This is sort of like Snell's law, if you ever studied optics in a physics class or something like that, and you studied refraction, the bending of light, which is electromagnetic waves, essentially at that interface between materials with different permittivities is basically what gives rise to refraction in Snell's law. So those are going to be our simple 1D electrostatic relationships, and we'll be making use of those next time when we talk about a p-n junction. Okay, so here we are looking at sort of the two mechanisms of the movement of charged particles that we're going to be concerned with in this class. The first one is called drift. Okay, and drift is the motion of charged particles due to the presence of an electric field, or in the presence of an electric field. The charged particles are experiencing a force due to the electric field, and that force accelerates them and they achieve a particular velocity, and charge times velocity is basically current. And so the drift current is basically proportional to the charge on each carrier and is the concentration of charge carriers. Mu is a parameter called mobility, and that is a constant proportionality between velocity and electric field. So mu e is basically the velocity which to which these carriers are driven by the electric field. And we depict this sort of situation on a picture like this. This is called an energy band diagram. And I guess I would call this a cartoon energy band diagram because we're going to be kind of a little bit loose here and qualitative. But basically what this is a picture of electron energy going up vertically here as a function of position. And because Ben Franklin didn't know about the sign of the charge of an electron, we have this negative charge on the mobile carriers, and so what happens is that higher voltage actually is lower down and higher electron energy is actually up on a picture like this. And so if we have, if you remember, the spatial derivative of the potential is basically the electric field. So when we have an electric field in a region, we have a tilt in these these lines of energy here. And what will happen is that the electron on a picture like this wants to go downhill. So what happens is if we see an electron, which I'm representing here as a closed or filled in circle, it's basically going to be moving to the right under the influence of this electric field, and the degree of tilt here is proportional to the magnitude of the electric field. And so I always think about the sign. I always think about the fact the electrons roll downhill. That's how I think about which direction the electrons are going to go in on a picture like this. The holes which have an opposite charge go in the opposite direction, and you can think of holes as sort of like bubbles in a fluid. Actually, that's a very good analogy to what holes are. Holes like to bubble up, so holes like to float up as high as they can on a picture like this. And so these two lines that are parallel here are actually the edge, the lower edge of a range of energies that conduction electrons can have. This top thing here is called the conduction band edge, and it's basically the energy of an electron that's free to move but has no kinetic energy. So it's just sitting there. It's free to move, but it has no velocity, so it has no kinetic energy. That would be the energy level that's represented by this line here. And like I said, if an electron is free to move and it has some velocity, it moves up off the conduction band edge to a different higher energy level in that range of energies, or band of energies. And then this range of energies down here is called the valence band, and this is where the electrons that are participating in covalent bonds all live. They all live in this range of energies down here. And it's also where the holes live. So the holes live in the valence band, and the conduction electrons live in the conduction band up here. And this energy in between here, this range of energies, is called the forbidden, or the band gap, or the forbidden band of energies. So electrons don't normally hang out here, holes don't normally hang out here. And this is roughly the gap between these two energy bands, is that 1.1 electron volts that I mentioned earlier for silicon. Holes bubble up and electrons go downhill on a picture like this. So the second type of carrier transport mechanism that we're going to talk about is basically diffusion. So you've probably seen this in a chemistry class or in Mat Sci or something like that. So this is basically just the motion, the random motion of particles with no preferred direction, probably due to the thermal energy that they have. If you like to think of it this way, from areas of high concentration to areas of low concentration, if like half of these go left and half of these go right at some time, half of these go left and half of these go right with no sort of preference for which direction they go in, more of these are going to go this way than these went this way, so we're going to get a net flux of particles from areas of higher concentration to areas of lower concentration, just because there's more of them over here moving in this direction than there would be moving in this direction from over here. And so unlike drift, where the sign of the charge on the carrier actually determines which direction it's going to go in this particular case the direction is in the direction of the concentration gradient for both, and it's the same direction if the gradient's in the same direction. So the diffusion current is also proportional to the charge on each carrier, but this current is proportional to something called the diffusion constant times the spatial derivative of the concentration. So this is the concentration gradient of the carrier. Now, you might think that these two things are completely separate from each other. It turns out that there is a relationship between these parameters, the diffusion constant and the mobility of a given carrier. At thermal equilibrium, it turns out that the ratio of D to mu is equal to kT over Q, where K is Boltzmann's constant, T is the temperature, absolute temperature, and Q is the charge. For us, it's the elementary charge, or the charge on an electron. And that kT over Q is something we're going to see again and again. It's called the thermal voltage, and so we give it a special symbol, U sub T. This is the thing that has a value of about 25 or 26 millivolts at 300 Kelvin. So kT is an energy. kT over Q is a potential, because potential is basically energy per unit charge, or work per unit charge. This is called the Einstein relation, and this is something that Einstein sort of figured out in his classic paper on Brownian motion, which I guess he figured out somewhere between special relativity and general relativity or something like that. So Einstein was noted for a bunch of different things: photoelectric effect, relativity. He had his hand in quantum mechanics. He also did some study of Brownian motion, and he found that this relationship between these two parameters hold at thermal equilibrium. So we're going to take some of this and do a little bit of stuff with it before we call it quits for this segment. So this will be a little bit longer, and there's a lot of stuff on this slide, so hopefully it won't be too bad. But what we're going to study here is a situation where we have a potential barrier. So we have two different levels of potential, psi 1 and psi 2, at different positions. So in this range of positions, say typically x1, the potential is psi 1, and over here we have a different potential. At x2 we have a potential of psi 2, and we have, let's say, a lot of electrons here at this lower potential, because the electrons like to go downhill, and we have relatively fewer electrons over here, and so there's going to be a tendency of electrons to diffuse from higher concentration toward lower concentration. But at the same time, we've got some change in potential here, which means that there's an electric field in this region, and so there's going to be a tendency for them to drift in this direction. And we'd like to see if in equilibrium we can find some sort of relationship that happens where we have drift balancing with diffusion. And so we can set up a drift current here, which is basically Qn mu E, and we can plug in for E minus d psi dx. And we have the diffusion current, Q d dn dx, and then we basically have like a Kirchhoff's current law type relationship where we basically sum these two things and they equal 0. And so we plug these things into our KCL-like equation here. And we can rearrange. So we can move this term over here to the right-hand side to get to here. And so we have d times dn dx is equal to n mu d psi dx. Then we can basically take the n downstairs over here and take the mu downstairs over here to get to here. So we have 1 over n dn dx is equal to mu over d times d psi dx. So we've separated variables here, effectively, and put the n's on one side and the psi's on the other side. And what we're going to do is we're going to integrate over space to get rid of the differential or the derivatives here. So we multiply both sides by dx, and we integrate from position 1 to position 2 on the left-hand side. We do the same thing on the right-hand side. We multiply by dx, and we integrate from x1 to x2. 1 over ut, we've plugged in for mu over d. Right, that's the Einstein relationship. Now this is a perfect differential here, and so we can actually change variables, and we can integrate on the left-hand side over n. So at position x1, there's some concentration of electrons, n1, and so that's what we get here for the lower limit. We substitute in and change variables to n. And over here at position x2, the concentration of electrons is n2, and so the upper limit of integration becomes n2. And we have 1 over n dn dx times dx, that becomes dn. So we have the integral from dn over n, or the integral of dn over n from n1 to n2. And on the right-hand side, we can do the same thing, only it's a little easier. So at position x1, the potential is psi 1, and at position x2, the potential is psi 2. So we're integrating here from psi 1 to psi 2, and d psi dx becomes d psi. And so the right-hand side is a very easy integral to do. It's just psi evaluated from psi 2 to psi 1. And so the right-hand side becomes psi 2 minus psi 1 over ut. The left-hand side isn't too bad either. It's basically the log, or the natural log, of n evaluated from n1 to n2, which is log of n2 minus log of n1, and we can use the property that the difference of the logs is the log of the ratio to write the left-hand side as log of n2 over n1. I guess I should say here that in this class, when I write log with no base, I mean natural log. So you may be used to seeing ln as natural log, and that's perfectly fine. I'll understand what you mean if you write ln. But if you're using MATLAB or using Python or some other language like C or Fortran, you'll find that the natural log is typically in the library, the math library, the function log. And so I've kind of gotten into the habit of just using that for the natural log. So that'll be the convention that I'm following in this class. So log to the base 10, I'll actually explicitly usually write log base 10, even though you may be used to seeing log as the common log. That's just the convention I'm going to use. So we can exponentiate both sides of this, and what we get is that the ratio of n2 to n1 is exponential in the height of this barrier divided by the thermal voltage. And so this ratio, or this relationship, is called the Boltzmann relationship. And this is actually where all of the exponential IV relationships that we're going to study this semester really come from, is this sort of the ratio of the concentrations here on either side of the potential barrier is exponential in the height of the barrier. And so you can think of this barrier, the height of this barrier here, as being controlled by the voltages that we apply in some ways, and then the number of electrons that are able to surmount the barrier is exponentially related to that applied voltage. Okay, so we'll see how that works together probably in the next segment or two to come up with the ideal diode equation. But this is sort of the underlying principle here. And so that's it for this segment. We'll see you next time.